Hi guys, welcome back to our flipped classroom. Today we're going to learn about L'Hopital's rule. So what we need to do is go back and look at limits like we did in chapter 2 again. So if I were to give you this limit as x approaches 3 over here, how would you solve or evaluate this limit? And you have to remember there were steps I gave you for how to evaluate a limit. So let's look at those. So the steps for finding a limit. You first have to determine what x is approaching. In this problem, x was 3. X is approaching a real number like I have here in step 2, so we're going to plug in 3 for all the x's. Now as I go through the examples today, keep these steps in mind because we're going to have to remember them. So let's, for this limit, simply plug in x is 3. So you plug a 3 in here and a 3 in here. You get 9 minus 9 over 3 minus 3. Your result is going to be 0 over 0. Now we've seen results like that before, and when you get a result like that, you used to have to proceed with the steps. And it says here above, but you know what I mean in your notes, those 6 steps. And then if you can't follow any of them, you have to get down to graphing or making a table. That was kind of annoying. So there is an easier way to solve these problems. Thank you, Mr. L'Hopital. Yes, he was a real dude. He was French. So what he did was come up with a rule to evaluate things like 0 over 0 or infinity over infinity. If you forget all the rules and you plug in and you get these types of things, that thing, 0 over 0, infinity over infinity, is what's called an indeterminate form. Again, if simply plugging in gives you something like 0 over 0, infinity over infinity, getting an indeterminate form, you can use a shortcut to evaluate that limits. Basically what I'm saying is you technically won't have to use graphs or tables anymore. So here's what L'Hopital rule says. You have 2 functions, f and g. You have to be able to calculate their derivative. If the quotient f over g has the indeterminate form like 0 over 0 or infinity over infinity when you plug in the number, then the limit of the thing I give you is the same as the limit of the derivative of the top and the derivative of the bottom. So again, here's what that means. If you get an indeterminate form after you initially plug in a number, all you have to do to solve that limit is take the derivative of the top and the derivative of the bottom and then re-plug the number in. So let's look at some examples. For example, if I want you to find the limit as x approaches 0 of this function, what you would first do is plug in 0 for all of the x's. So you need to know what the cosine of 0 is. You need to know 2 times 0, and then you need to know 3 times 0. You have those. But the cosine of 0 is 1. So now what happens is this one cancels with that one, and you get the limit of 0 over 0. Well, you can't do that. That's technically not allowed. And in the old days, we would have to try to do some algebra on this to simplify. If we couldn't do that, we would try to graph something. And if we still couldn't do that, your last resort was a table. But now we know L'Hopital's rule. So if I take this same exact limit and take the derivative on the top and the derivative of the bottom. The derivative of cosine is negative sine. The derivative of 2x is 2. The derivative of minus 1 is 0. Then take the derivative of the bottom separately. You are not using the quotient rule in these problems. You're using a shortcut to evaluate these limits. You're doing it by the derivative of the top and the derivative of the bottom. So the derivative of the 3x is separate. It's just 3. Now, according to L'Hopital's rule, since you took the derivative of the top and the bottom separately and left the top on the top and bottom on the bottom, now you can plug in 0 again. If you do that, the sine of 0, you should know, sine of 0 is 0. So negative 0 is just 0, plus 2. On the bottom, you still get a 3 because the limit of a number is that number. And so your final solution is 2/3. If we were to graph this original function or make a table or do whatever we needed to do the old way before this rule, we would eventually see 2/3 was the answer. But Mr. L'Hopital made this a lot easier. Let's look at another one. Another trig function. Now in this one, this is a left-sided limit. You're going to see why in a second. So you can use L'Hopital's rule even if you're finding a limit from the left or the right, not just the full limit. So if I go ahead and try to evaluate this with a pi over 2 plugged in, let's see what happens. You get 4 tangent of pi over 2 over 1 plus secant of pi over 2. Now you need to know what the tangent of pi over 2 is. You could just type it into your calculator, but you're going to get like undefined or something like syntax error. It's because you need to know what the graph of tangent looks like. Here it is. As you approach pi over 2 from the left-hand side, this goes to infinity. The same thing for the secant. You're going to need to know what its graph looks like. Here's the graph of secant, here's pi over 2. As you approach from the left-hand side, you're also going to infinity. So that would mean you're going to have 4 times infinity for the top, again replacing the pi over 2 with this tangent, approaching infinity with that infinity, and the secant of pi over 2 going to infinity on the left, replacing that with infinity. You're going to get infinity over infinity, another indeterminate form. But with L'Hopital's rule and a little bit of pre-calc, this becomes a really easy limit to evaluate. So first, take the derivative of the top. So you'd have 4. The derivative of tangent is secant squared. The derivative of 1 is 0. The derivative of secant is secant tangent. Now I want to evaluate this, so I'm going to need to do a little bit of pre-calc. So first, I'm going to cancel out that secant with that one. There are 2 on the top and 1 on the bottom, so I can cancel them. So I'm down to this, 1 secant over 1 tangent. Now what I want to do is simplify that even further if I can. So what I'm going to do is replace secant with its definition 1 over cosine, and tangent with its definition sine over cosine. Now if you do outies and innies, flip and multiply, or the shortcut where the denominators are equal, they match, you're going to reduce this. So that cosine and that cosine cancel, and the whole thing reduces to 4 over the sine of x. Now, after you do all of this algebra, remember this first step was taking the derivatives. Do all of this algebra or pre-calc work down to here, try plugging in the pi over 2 again. And when I do that, the sine of pi over 2 is just 1. And you should know that from your unit circle. You could type it into the calculator if you need to. 4 over 1 is 4. So this limit all the way over here is equal to 4. Here's all the work that goes with that. But again, if I couldn't plug in the pi over 2 like we had over here, I would have to resort to either a graph or a table or some really complicated pre-calc in order to get to the solution. The easiest way is to just use L'Hopital's rule, take the derivative on the top and the bottom, pre-calc it up, and you'll get to your final solution. Now, we do use this a lot with trig functions because, again, I really don't want to have to graph complicated ones. But you can use it with any function as long as that initial plug-in yields an indeterminate form. Something else that I did not write down in your notes you should add, that's why I have it in red here, you can also use this rule as many times as necessary to get you to an answer. And I'm going to show you that in this example. When I first initially plug in infinity here, I'll get infinity on the top and infinity on the bottom, an indeterminate form. But if I go ahead and take the derivative of the top and the bottom, I'll get 3x squared plus 1 over 9x squared. You're supposed to be able to just plug in the infinity again. But if I do that, I'm going to get infinity on the top and infinity on the bottom. So I already took the derivative once here, but I'm going to apply L'Hopital's rule again. So take the derivative again. The derivative of this is 6x. The derivative of this is 18x. Now you could either simplify these x's out, because plugging in infinity once again gives you infinity over infinity. But just for the sake of argument, I'm going to show you that you could take the derivative another time, and the derivative of 6x is 6, the derivative of 18x is 18, and now again the limit of a number is just a number, and that number simplifies to 1/3. Now, this was just an example to show you how to use L'Hopital's rule, let's see, 1, 2, 3 times to get to an answer. You're totally allowed to do that. But couldn't we have gone all the way up here? And as we approach infinity, don't forget those rules for limits. You could have divided everything by the highest power of x in the denominator and canceled. You could have also used the rules for pre-calc that say that if these exponents are equal, the answer is the ratio of the lead coefficients, 1 over 3, same as 1/3. But I wanted you to see one where you got infinity over infinity and then one that required you to use the rule 1, 2, 3 times so that you knew you could use L'Hopital's rule as many times as necessary to get your answers. So when you get to class next, you'll have a worksheet showing that you know how to do this and you'll get to practice these skills on your own. See you next class.